השאלה אם זה יהיה כאן או אני לא אומר שזה לא חשוב. המשקים, אני אומר שזה לא טריוויאלי
יכול להעביר אחד שניים רגע? רואים קצר?
שזה יהיה בפקולטה. יכול להיות שזה יהיה בפקולטה אחרת.
תודה.
אני אדבר באנגלית בכל מקרה, כי אחרת יהיה לי תרגום סימולטנית לועזית כל הזמן. אבל אם אתם, כן, ואם אתם רוצים לשאול שאלות בעברית, אתם מוזמנים. טוב, נתחיל.
אז כן, אז רק נגיד שאנחנו שמחים לארח את אריאל, רק שם, מ-CMU.
תודה רבה. Happy to be here. Yeah, very formal. Awesome. Okay, so I want to tell you today about an approach that I'm really excited about, that I've been calling virtual democracy in recent years, in the last year or so. It's about automating ethical decisions in AI using machine learning and social choice on a very high level. So let me start with a bit of context for this approach, kind of historical context. So as you know, democracy needs no introduction. It dates back to ancient Athens, where people would use what's called direct democracy. They would get together in the same place, the citizens, and they would vote directly on the issue at hand, or the issues at hand. A few thousand years later, like 30 years ago, people in the dawn of multi-agent systems, which is this area that thinks about software systems populated by autonomous heterogeneous agents, they thought that direct democracy might also be a good way of automating decisions in a system like that, where the idea is that the agents have their own opinions and preferences, and we aggregate them by basically having an election. So this was the underpinning of the study of computational social choice within AI for a couple of decades. But a couple of years ago, myself and a couple of other people started saying maybe the killer app of this area is actually helping people and not software agents make collective decisions. So I founded a couple of websites that are supposed to help groups of people make decisions, and a couple of people in the community have founded additional websites. So this seemed like a really great application of these techniques developed in this area of computational social choice. The irony is that what I want to tell you about today goes back to the picture on the right. So we're going to talk about elections where the voters are software agents. They're going to be models of real voters, but they will be software agents nonetheless. Okay, so we're going to focus today on the picture on the right with agents as voters. And I'm going to focus on telling you about the approach in two particular domains. The first is autonomous vehicles, where the type of ethical dilemma we'll want to decide is a car gets into an inevitable accident, which people should live and who should die. It's a very weighty ethical decision. The second domain is food rescue, where the ethical dilemma is given a food allocation, which recipient organization should receive that allocation. So it's also a very value-laden dilemma that involves considerations of efficiency and fairness. Good, so I'm going to start with the autonomous vehicle domain. This is going to be based on joint work with my student Ritesh Nutigatu, my colleague in the CMU machine learning department, Pradeep Ravikumar, and a team of collaborators at the MIT Media Lab led by Iyad Rahwan. But before I start, I want to make a caveat. So I've given some versions of the talk in the past. In fact, Ishai heard some version of this talk. And what I've noticed, including in that talk, was that people are generally pretty happy until I mention autonomous vehicles, and then the audience becomes an angry mob and all hell breaks loose. So what I want to tell you is, keep calm. You will have philosophical objections when I talk about self-driving cars, and some of them will be grounded. What I want you to keep in mind is that you should think of this first part of the talk as a proof of concept that I think is also very useful for pedagogical reasons. So we'll see how it illustrates the approach and contrasts with the second part of the talk as well. And what I would recommend is waiting with some of the philosophical objections until the second part of the talk, because I think that will answer some of the questions you might have. Okay, so with that, let's start. The starting point for this is this classic problem in philosophy called the trolley problem. So in its most basic version, there is a trolley speeding down a track, and there are 5 people tied to the track. And you control a switch. If you flip the switch, it diverts the trolley to an alternative track where only one person is tied. And the question is, would you flip the switch? Would you take this action and sacrifice one person to save 5? So the trade-off is good in terms of numbers, but you have to take this active action to make it happen. Over the years, people have, philosophers have agonized over many variants of this problem. So in one variant, there's an overweight man standing on a bridge, and you can push this man off the bridge. He will stop the trolley with his body and die in the process. So again, it's sacrificing one person to save 5, but it's taking a very gruesome active action to make it happen. A relatively easy variant, I think, is the one where this overweight man is actually a villain who's the one responsible for tying these 5 people to the track. So would you push this villain in order to save the 5? I think this one is pretty easy. But a difficult one is, again, you control a switch. But now if you flip the switch, there's another trolley that moves towards the first one, and they collide. So far, nobody died, and you saved the 5 people. But as a result of the collision, one of the trolleys flies miles in the air and lands on some unsuspecting person who's sleeping in a hammock in his backyard miles away. Right? So would you kill this completely unrelated person in order to save the 5?
So what does today law say? So if you go by US, Pennsylvania laws.
Yeah. So, yeah.
I assume you are not allowed any of those alternatives, right?
I mean, so there are, in the US, there are no laws for self-driving, for this kind of dilemma.
This is not self-driving.
Oh,
You're saying, I'm making
right.
a decision.
Yeah. So right. As far as I know, the laws don't constrain you from, choosing among these alternatives. I think what's more relevant is people have started thinking about it.
That's constrained.
I mean,
I think if I cause someone to die, I'm guilty.
right, but
If I didn't do anything,
right.
those laws are anything.
Yeah. So here, I mean,
Also with Samaritan laws in some states.
yeah.
But
So,
this is not good Samaritan.
so
Killing one person is not good Samaritan.
okay, yeah, so this is the type of philosophy I don't want to get into, but let me just make one quick comment, which is in Germany, they did start developing a legal framework for this. For last year, they developed they had a commission with lawyers and so on. They developed a framework, and what they said is you should prefer people to animals, that's the only thing, but there's no preference for numbers, and you can't take into account any other personal feature. Okay, so this is after the laws were processed in this context, this is what they came up with.
There's no preference to numbers?
There's no preference for numbers.
Okay. So this doesn't solve any of the...
No. Okay, so our collaborators at MIT, what they wanted to understand is how people make this type of decision, and the reason is that this type of dilemma, as we were just discussing, does come up in the context of self-driving cars. So for a self-driving car, what happens is the car gets into an inevitable accident, let's say because of a brake failure, but it does have the computational capacity to possibly make a decision of this type, and then people have been discussing what should it do. So in the website, visitors are faced with pairwise dilemmas or pairwise judgments.
Whatever the law says, if you're driving the car, then if it's a brake failure, then you can do whatever and you're okay? Or
I don't think the law covers that specifically, but I mean, it's very dependent on countries, so I don't want to give a definitive answer on that. I mean, as far as I mean, what I know almost definitively is that the law doesn't decide this. It's not that you can rely on laws and they would tell you exactly what to do on these trolley-like problems. So whatever guidance it gives, it can't give you sufficiently fine guidance in order to solve the problem. Good. So you get these pairwise judgments. So here's an example. What we asked to choose between is a situation where the car drives straight and kills 3 pedestrians crossing on a red light. And you can get information about one of them. Here, one is an overweight man, one is a male doctor, and one is a baby. Or you can swerve and hit a roadblock, thereby killing all of the passengers, and you can get all of the information about the passengers. In particular, there's 5 of them. What would you do? So this is a difficult dilemma, and Iyad and his team have been able to really engage people with this type of decisions. When we collaborated with them starting in 2016, they had 18 million pairwise comparisons like this from 1.3 million people. By the time they finished the experiment last year, they had 40 million pairwise comparisons, and they published a paper in Nature with the results of the experiment, how people at least some features that people take into account or care about when they make these decisions. But the starting point of our collaboration was the realization that we can actually use this data set in order to not just understand how people make these decisions, but to automate them. And this was the starting point for this virtual democracy framework. So I want to tell you on a very high level what it looks like, and then we'll dive into the steps in a bit more detail. So the first step is data collection. And the idea here is that we collect preferences from people who will later be voters on the type of dilemma that we care about, and we do it as pairwise comparisons. So this was done by our MIT collaborators in the autonomous vehicle domain. This is the moral machine dataset. Step 2 is learning, as in machine learning. So the idea here is that we build a model, we learn a model for the preferences of each person based on the data that allows us to predict their preferences even on dilemmas that we haven't seen before. Step 3 is summarization. The reason we need this is that we need to make decisions in a split second. And we can't afford to go back to the 1.3 million models and consult all of them. So what we do is we build one concise model of societal preferences that we can work with very quickly at runtime. Finally, the most interesting step is the aggregation step that happens at runtime. So this is where the democracy and social choice actually happens. The idea is that ideally what I would want to do is I'm facing at runtime a bunch of alternatives, let's say 10 or 100, any number. I would want to go back to the 1.3 million people, to the voters, and ask them, what would you do in the current situation, on my current dilemma? And then I would get their preferences in the form of, let's say, a ranking. So they tell me this is the most preferred alternative, second choice, third choice, and so on. And then I would aggregate all of these rankings, all of these votes, using a voting rule in order to make a decision for the system. That's the ideal. Of course, this is completely infeasible. I can't go back at runtime to these 1.3 million people. So instead, what we do is we use the models that we've built to predict what these people would have wanted to do in the current situation. And then we aggregate the predicted votes in order to make a decision. So essentially, we hold a virtual election with these virtual voters who are the models of the actual voters. Okay, this is the key idea behind the approach. So we've implemented this pipeline for the auto. Yeah.
So the voting rule in the last session is orthogonal to all this process, right? And you aggregate everything, but then orthogonally you have to choose a vote.
Right. So the whole process gives me predicted preferences for the voters. Then I have to aggregate them in however way. We'll talk a bit about what's a reasonable way to do it.
You said that you're training a few models. So, it's kind of has to do with gerrymandering, the question of how many people do you fit a model to, how many models do you choose, which model?
So we have a model for each voter individually.
For each voter individually?
Yes. I think that this would be a great point if we, and we'll see that there's some of that happening in the autonomous vehicle domain where there is the summarization step, but there's only one model for everybody. If there were models for subsets of voters, then you might get a gerrymandering kind of effect. But it's kind of very binary. So we'll see in the next domain, we'll have no summarization. There'll be individual models. Here we'll just have one summary model for everyone.
Can you explain how you do the summarization?
Oh yeah, we'll get to that in a minute. I actually won't go into details because it's not super interesting and won't be relevant later. I'll just tell you what it means in a few minutes. Okay, so what I'll do next is I'll dive into the details. But let me just say that on a high level, we've implemented this pipeline. And it led to a system that can make decisions of the type that is made on moral machine. Okay, so it did lead to an implemented system that is effective in doing these decisions very fast. So what I want to do in the next 10 minutes or so is just go into a bit more detail on each one of these steps, and then that will answer some of these questions. So step 1, data collection. Like I said, this is the moral machine data set, so there's not more to say. Let's talk a bit about learning. This step is actually very much off the shelf. There's nothing interesting going on here, so I'll talk about this pretty briefly. What we do is we use a classic model from statistics called the Thurston-Mosteller model. The way it works is for every voter, you have this model where each alternative, among the current alternatives we're facing, we have a mean utility for that alternative. And when we want to compare, when the voter compares a pair of alternatives or gives a ranking over the alternatives, we take a sample of utility for each alternative from a normal distribution around the mean. So in this example, I might take a sample from the red distribution, a sample from blue, a sample from orange. This would give me the ranking blue above orange above red, even though the orange mean is higher than the blue mean. Right? That can happen with some probability. Now, the means are represented using this linear parameterization. So we have a parameter vector beta, and we have a feature vector xi for each alternative. The features in moral machine are the following. They're whether we have pedestrians or passengers, if pedestrians, whether they're crossing on a red light or a green light, did we take an action and swerve or drive straight, and information about the characters. So there's a character count and how many characters of each type. And then, the beta vector, you can think of it as a weight for each feature. So you take the dot product of these two things. This gives you the mean utility, and that induces a probability for each ranking or each pairwise comparison. And the goal is to learn the beta vector from pairwise comparisons. Okay, so this is pretty much off-the-shelf learning to rank stuff. Now,
These pairwise comparisons that you ask people to do, are they usually consistent? They're transitive?
Right, so in moral machine, I actually don't have a definitive answer for that. We actually never had access to the data itself, so that was handled by Yad and his team. We gave them the training, they trained the models. What I can say is that in moral machine, I wouldn't expect them to be consistent because these 1.3 million pretty random visitors to the website. For example, I have visited the website many times to show the website to people, and I just do kind of random pairwise comparisons. I'm sure many other people just play with the website. So I would expect that the data is not very trustworthy. And this will be in stark contrast to what we'll see in the food rescue domain, where the data we'll also see like very good accuracy results. I would expect this data to not be generally transitive, for example. And that's why you do need a statistical model that deals with the fact that you might not have transitivity. Okay, so one more point to connect learning to summarization. So we think of each Thurston model like this, as a distribution over rankings. So in this example with 3 alternatives, the highest probability is for the ranking orange, blue, red, and this is what you're seeing over here. But then there's also some probability of switching blue and orange, and that would give you this ranking over here. Or, with some probability you would switch blue and red, that would give you this ranking over here. This is a lower probability. And there's also some small probability for the other rankings. I didn't even explicitly mark it in the illustration. Okay, so this model induces some probability for each possible ranking over the alternatives. This is voter 1. Voter 2 has a different model that induces a different probability distribution over rankings. So we think of each voter as corresponding to a probability distribution over rankings. Okay, so what is summarization? Like I hinted before, I just want you to get the idea of what summarization is, not how we do it, which is not very interesting, and we won't do it later. So, think again of this example with 2 voters. What I'm really interested in is this, what we call a preference profile or just a profile, which is the average of these different distributions. So the way to think about it is this is what would happen if I took a random voter and then I sampled the distribution of that voter to get a ranking. Right, this would be the distribution of the rankings, and it's obtained by just averaging all of these probabilities. You can check that, if I didn't make a mistake, the bars should be the average of the bars on the left and the right. Yeah.
Statistical model for each voter of the 1.3 million, or
Yeah, so initially we built a statistical model for each voter of the 1.3 million, but in this application we don't want to use them at runtime. So what I'm doing now is avoiding that by building one model for everybody.
In the initial part you built...
Yes. So in part 2, in the learning step, we build a model for each one of the 1.3 million. Okay, but so far all of this is happening offline, so we can afford to spend time.
Would it be different if you just learn one voter for everyone? I mean, the learning phase.
Yeah.
Would it be completely different?
So I don't know. You could do the following thing, like take all of the pairwise comparisons of everybody and learn one model for everybody. I think that would be, a reasonable approach.
I mean, one more natural approach is maybe to learn clusters. Like you assume that there are several clusters, and people have similar idea in a cluster.
Yeah. I think all of these variants are reasonable. So one thing I will say is that this particular way of doing things leads to a very nice guarantees on the next slide. So that might, give a partial answer to your question. Moreover, like I said, in the next application, we won't do any summarization at all, so we'll stay with all of the individual models. So this part is pretty specific to this particular application where things have to happen very fast. That said, I'm not completely ruling out doing things that way. You would have to rethink how you do aggregation. So after I talk about aggregation, it will give you a bit more context. Okay, so what is summarization doing? Remember that for each voter, the distribution was induced by a Thurston-Musteller model. Now, and remember that what I'm interested in is this profile over here. So what I ideally want to do is summarize all of these Thurston-Musteller models as a single Thurston-Musteller model that would induce this distribution that we have in the profile, this average. No, it's not. So that's a point. This is why these arrows are dashed, right? So you can't summarize individual Thurston-Musteller models with a single one, and you can't do it in a way that would induce this profile. So what we do is we hope to do it in a way that approximately gives you this summary profile. And we have some empirical results on the moral machine data set that shows pretty good accuracy for this summarization step. But there are no theoretical guarantees about this in this application. Okay, but what I want you to take away from this is that after this step, we have this one Thurston-Musteller model that approximately induces some distribution over rankings that is approximately the one that we want.
You take the same distributions in the same?
Sorry? Yeah. So we take the same we take the exact Thurston-Musteller models and we directly summarize them to get a Thurston-Musteller model. We never look at these when we do the summarization. We look at the models. They have each voter has a parameter vector, and we use them in order to get a single parameter vector that is the Thurston-Musteller model that we then save as the model of societal preferences. Okay. Okay. So the most interesting step is aggregation, and so let's talk a bit about that. After the last step, we have the single Thurston-Musteller model that induces a distribution over rankings. And we think of this as the model of societal preferences. So we can think of this for each ranking as the fraction of voters that are associated with that ranking. Now, what we want to do is take this object and aggregate it to get a single decision. So over the centuries, hundreds of voting rules have been proposed. Let me just give you two examples to make this more concrete. One example is due to Jean-Charles de Borda, the Chevalier de Borda from the 18th century. And what he said was, if we have m alternatives, every voter will give m-1 points to the first place, m-2 points to the second place, and so on, down to 0 points to the last place. With three alternatives in the example, it would be 2, 1, and 0. So here, blue, for example, would have 0.6 times 2 plus 0.4 times 0, which is 1.2 points. Orange would have 0.4 times 2 plus 0.6 times 1, which is 1.4. You can check that red has 0.4. So here, orange is the best alternative according to Borda count. The voting rule is called Borda count. A second example is even older. It dates back to the 13th century and Ramon Lal. And what he suggested was, for each alternative x, we will give it a point for every other alternative y, such that a majority of voters rank x above y. So in the example, blue is ranked by a majority above both orange and red, so it has 2 points. Orange is ranked by a majority only above red, so it has 1 point, and red is not ranked by a majority above anybody. A majority, of course, is 0.5 here. Red is not ranked by a majority above anybody, so he has 0 points. So according to Lal, blue should be the winner of the election. Right? But these are just two examples. Like I said, over the years, over the centuries, over the millennia, hundreds of voting rules have been proposed. And the big question is, which voting rules should we use? Right? This question came up before. I think Michal asked it, right? How do we, this thing is kind of orthogonal to everything that happened before. Which voting rule is the correct one? And this question is actually twofold from my viewpoint. There are two sub-questions. One is, how do we apply the voting rule very fast again so that we can make a decision in a split second? And second, which is more vague, which voting rule is the most ethical? Right? We kind of want to make ethical decisions. Which one would give us the most ethical outcomes? Yishai.
So, okay, if we're thinking about the Bordeaux rule, right, so you can give them like three alternatives, 2-1-0, or 3-2-1, or 10-9-8.
Yeah.
Technically, it should be the same.
It is the same.
I'm willing to bet any amount that if you give those, you see very different results.
I mean, it's technically,
Technically it's the same, but people will behave
oh,
differently.
but people don't actually,
Giving zero.
yeah.
No, but
People don't give
choose,
points.
they just rank.
Yeah, people don't give points. They
You
only,
do it.
exactly. So people give a ranking,
I see.
and this happens in the background. So this is transparent.
And if you ask people to give points,
So there are different systems that actually ask people to divide points, but I've never seen an example where you ask people to give points, 10, 9, 8, 7, because it doesn't make sense, right? It just asks them for more information that you don't need compared to giving a ranking.
see, like behavioral economics would say framing the question
Yeah.
has a huge impact on what you see
Yeah,
later.
plus I've never seen anything in this direction. It's possible somebody looked at, but at least for this application, it doesn't matter, right? Because, I mean, in this application, people don't even get to the stage where they rank. All they do is give pairwise comparisons initially, and then that's translated into predicted rankings and so on. So technically, it will be the same.
Okay.
Okay.
Behavioral economics would be the same.
I mean, yeah, but
Because you do have a framing issue here. How do you pose the question, and how are they?
so the only question I pose to people is, here are pairwise comparisons. What do you prefer, this alternative or this alternative? And that goes through the whole pipeline and becomes rankings, and then I run this algorithm in the background.
You randomize the order, I guess, when you show them to people? The two...
For the, oh yeah, what you see left and right, yeah. I mean, both of them are generated IID, so there's no point in it.
Shai's point is, I think, if you tell them the whole process and you tell them vote
Yeah,
rule, they might strategize in the pairwise
But the pairwise comparisons are so far removed from the actual, from the part where the voting happens that, maybe a behavioral economist would disagree. I find it like very hard to believe that this, the framing, even if I frame Bourda in different ways in that step, would actually affect how they do pairwise comparisons.
So it's not clear to me even if you do left, right, or top, bottom, you'll see the same
Yeah.
results.
I mean, I actually haven't committed yet to Bourda count, although we'll see in a minute that here things are much more general, but Bourda count will come later. Okay, so the second question is, which one is the most ethical? And the really interesting point here is that for this particular application, under the assumptions that we made, we can actually give a very satisfying answer to both questions. So I'll just state a special case of the theorem that we prove. That if we have profiles that are induced by a single Thurston-Musteller model, represented by a parameter vector beta bar, then any voting rule satisfying minimal properties, monotonicity and neutrality, would select an alternative that maximizes the dot product of beta bar and the feature vector xi. So what this tells us is that A, we can compute the outcome very fast. All we need to do is compute these dot products. And B, all of the reasonable voting rules would actually coincide. Right? All of those that satisfy monotonicity and neutrality, which are almost all of them, including Bourda and Lal, would select the same alternative. So we actually don't have to worry about which voting rule to use. The only reasonable thing to do is to take this dot product and take the alternative that maximizes this dot product.
I'm sorry, isn't the previous slide a counterexample to this?
No, so,
Because these are both...
no, but this is not induced by a Thurston-Musteller model, so this is just an example.
the 0.06.
Yeah.
Okay.
Yeah, so in particular, I don't want to go into technical details here, but we need a particular property called swap dominance compatibility, which means that, in particular, the best alternative should be such that for any other alternative, let's call the best alternative A. For any other B, any ranking where B is ranked above A, if you take the same ranking and swap A and B, you would get a ranking that has higher probability. Okay, and this is not satisfied by this particular profile. Okay, good. So,
What's the neutral voting?
neutral is one that doesn't care about the names of candidates. So if I called, Alice Bob and Bob Alice, it would just permute the outcome. And monotonic means that if I improve an alternative, it only helps it. And neutrality is actually the weaker assumption. Monotonicity is something that is not satisfied by some voting rules like STV, but it's still a pretty weak assumption. So, this is really cool, but it's very reliant on the assumption. This goes back to some of the things we discussed. It's very reliant on the summarization step. So we summarize things in a very lossy way with a very particular structure that satisfies this swap dominance compatibility, and this leads to this result. What we'll see in the next application is that we will forget about summarization, and that will in particular make us rethink aggregation. So we'll have to rethink this step. But I guess, going back to Michal's question, in this case, it's not completely orthogonal, right? Because the structure of this answer relied on how we did summarization. It will be more orthogonal in the next application.
Relies on what particular component of a
The fact that we think of the whole preference profile as induced by a single Thurston-Mosteller model that induces profiles with a very particular structure satisfying some properties like this swap dominance business.
But swap dominance is all you need? Any
Yes.
model that would...
Yes, so the more general theorem is about swap dominance, and then we see that other statistical models also satisfy swap dominance, but it's still a very strong property. In fact, it's so strong that it was never defined before in the social choice literature, because it really, it's a very, very strong assumption, which leads to trivial things like what we saw from a social choice viewpoint. Good, okay, so let's talk about the second application of food rescue. I have until 2:10. Is that usually how it works, or until 2?
Yeah, 2:10.
Okay, cool. Yeah, I think, this shouldn't take a lot more than 20 minutes, but I say we have a very lively audience with a lot of questions. So. Okay, so second application, food rescue. This is joint work with my students Anson Kang and Ritesh Notigato, my postdoc Alex Psomas, who just finished and is joining Purdue, and an HCI researcher at CMU by the name of Min Kyung Lee, and a team of undergraduate researchers that she has worked with over a year and a half. The starting point for this application is an organization in Pittsburgh called 412 Food Rescue. What they do is they receive food donations from stores and supermarkets, and they match them with recipient organizations, which are things like soup kitchens and food pantries and other nonprofits. Once they decide on the matching, they coordinate volunteers that pick up the food from the donor and deliver it to the recipient. The problem, which is also a good thing, is that over the last couple of years, they've grown drastically. At this point, they have hundreds of donor organizations, hundreds of recipients. It's around 550, I believe now, and thousands of volunteers. But they still have only 6 employees, and at any given time, only one dispatcher, who's the one who decides on the matches and coordinates the volunteers. And on a busy day, they get something like 100 donations. So this is a huge workload for a single person, and they've noticed that the quality of decisions degrades because of this workload. So they've been looking for ways to at least partially automate this process, or at least get recommendations on what to do. And what we realized at some point, they were in touch with Min for a couple of years now, we realized that this virtual democracy approach could be a very compelling approach to address this problem. However, there are several differences in how we apply the approach here compared to the previous settings. Some of them I hinted at. So first of all, for step 1, the data collection, before we had the 1.3 million anonymous moral machine users, now we're going to focus on stakeholders in 412 Food Rescue. I'll go into a bit more detail in a minute, but these are people who care deeply about the organization and are very thoughtful about how they give their data. So it's very different from what we saw before. Step 2, which is learning, both of them are off-the-shelf learning to rank, nothing interesting happening in both cases. Summarization, like I said, before we needed it, now we don't. Right? Because now, A, time is not of the essence. If it takes a few seconds to make a decision, that's fine. B, we're going to have only a few dozen voters instead of 1.3 million. So we don't need this. And as a result, we need to completely rethink the aggregation step, which we will do in a couple of minutes. So just to be clear, we forgot about summarization. So now the approach has only 3 steps: data collection, learning, and aggregation. And this is how I think of the canonical form of the approach. So I think for most applications, we won't need summarization, and these will be the 3 canonical steps. Okay, so I want to tell you about each one of these steps. Data collection, before we didn't have to worry about it. It was moral machine. Now we have to do it. The first question is, who are the voters? And like I said, these are stakeholders in 412 Food Rescue. There are 4 groups. The first is employees in the organization. So we have 3 participants who are employees. The second is representatives of donor organizations. We have 6 participants from this group. The third is representatives of recipient organizations. We have 8 participants from this group. And the last is volunteers, who are the people who drive the food around. We have 6 participants from this group for a total of 23 participants.
Why these numbers?
These are just, so we reached out through 412 Food Rescue to these different groups, and these are the people who volunteered. It could be...
So it doesn't mean necessarily that you want to put more weight?
No, it's actually an orthogonal question. It's not something I'm covering explicitly, but there is the question of when you do aggregation, how much weight you want to give to each group. And we actually asked all of these people how much weight we should give to each group. We took the average of the weights that they gave, and everybody gave the lowest weight to the donors and the highest weight to 412 Food Rescue. So including the donors. So we ended up with like almost 50% for the 3 employees in 412 Food Rescue. Basically, we divide the weight equally among the people in each group. Okay, so the weights ultimately in aggregation are not equal, and it depends on what these guys want. Okay, but the numbers are, what we wanted is at least a few people from each group, but it wasn't crucial exactly how many. But the really crucial point is these are all people who care deeply about 412 Food Rescue, are very thoughtful, like I said, and have been willing to spend hours and hours coming into more and more workshops and experiments and so on, gave very detailed feedback. So it's a very, very different situation from the world machine situation. Okay, the next question is how do we collect data? So it's again pairwise comparisons, but the key question is how do we identify an alternative? To be clear, an alternative is the set of alternatives is the set of recipient organizations. So when a food donation comes in, we have to decide which recipient organization should receive it. And the question is, what are the features that identify a recipient organization? So fortunately, Min has been working with 412 Food Rescue for a couple of years, and she has a previous paper in CHI 17, CHI is the main HCI conference, where it's just interviews. So she interviewed the stakeholders and asked them, what do you care about when we do these allocations? And that was incredibly useful for choosing the features that we use in this application. So the features are as follows. The 4 ones on the left are things that more or less stay fixed for each organization over time. The size is the number of clients served by the organization. Level of food access in the neighborhood, which is something defined by USDA, the Department of Agriculture. Income level in the neighborhood and poverty level in the neighborhood. The features on the right are things that change, that are specific to this donation. So it's the travel time between the donor and recipient, when was the last donation the organization received from 412 Food Rescue, and how many donations they received in the last 3 months from 412 Food Rescue. Right, so once you have these 7 features, these identify an alternative, and now we can ask for pairwise comparisons by identifying the alternatives with values for these features. So that's what we did. We collected at least 100 pairwise comparisons from each participant. By contrast, on Moral Machine, it was less than 13 on average. And again, much less thought was put into them. Moreover, some participants actually wanted to further refine their model and asked to give even more pairwise comparisons, which they were able to do through a web app that we gave them. So these are really people who spent a lot of time, caring and refining their models and really thinking this through. Okay, and I think this has led to pretty accurate learning. So the learning happens the same as before, but what I do want to show you here is some results about the accuracy. So what you're seeing here is a subset of 14 stakeholders. The reason I'm showing you these 14 is that for these 14, we built 2 different models. One is the machine learning model from the pairwise comparisons. The other is what we call an explicit rule model, where we asked them to manually build the model as follows. We told them for each feature, and each value of the feature give a number of points to that value. So it's like how many points does the recipient receive, the alternative receive, if the value of the feature is this. And then by summing up the points over the features, you get a score for each alternative. And then you can rank or compare alternatives based on that. And we checked the accuracy of both models on fresh pairwise comparisons. I expected the machine learning model to be more accurate, and this was indeed the case. Actually, the manual model was more accurate than what I expected. It did surprisingly well. So what we're seeing on the y-axis is the accuracy on pairwise comparisons. And the red bars are the machine learning algorithm. The blue bars are the explicit rule. So you can see that generally the machine learning algorithm is doing better, except for a couple of outliers. It's on half of the cases, it's getting better than 90%. It's doing well in general, except for 2 outliers on the right. But like I said, the explicit rule is also doing reasonably well. Now, an interesting step was that at some point, after explaining the whole process and showing them how the models behave on new comparisons, we asked the participants to choose between the 2 models. And out of these 14, 9 chose the machine learning model. So these are the ones where the red bar is now striped. And 5 chose the explicit rule model, including the 2 where the machine learning model was especially inaccurate. But overall, I was pretty happy to see that the majority did choose the machine learning model. For the ones that chose the explicit rule model, that's actually the model that we use in the implemented system. So we gave them the choice. For those that didn't participate in this step, we just used the machine learning model. Okay, so the last step is aggregation. And like I said, we have to rethink it. So let's start from scratch. Let's look at a small example. We have some true profile, which is the true preferences of these 3 voters in a world where there are only 4 alternatives. So if I went back and asked the voters, what's your ranking over the alternatives, they would say this. Unfortunately, this is not what we're saying. We're getting noisy estimates of this true profile. Maybe for voter 1, we got it almost right, but we flipped the first 2 alternatives. And for voter 2, we got it almost right, but we flipped something else, and so on. So these are reasonably good estimates that make some mistakes. And I think of this as the noisy profile. This is the input to my voting rule, not the true profile. So one question we asked ourselves is, what's a property of a voting rule that we want in this particular situation, right? When we apply things to a noisy profile instead of the true profile. And the property we came up with is the following statistical robustness property. So we want the output of the voting rule from the true profile to coincide with the output of the voting rule when it's applied to the noisy profile. In other words, we don't want the noise to ruin the output of the voting rule. Here I'm going to think of the output as a ranking. So the requirement is pretty stringent. I want the exact same ranking in both cases.
Both, you mean true and noisy?
Yes.
The noisy,
I think your intuition is maybe that this would be impossible to get because things can be very close, and that's absolutely true. So, let me.
You assume random noise, or you assume
noise is this, as I'll tell you on this slide. Right. So the big question is, of course, like to make this concrete, the question is what is noise? So let me answer that question, then I'll get back to Ishai's question. Okay, so what is the noise? The noise model is a classic model called the Mallows model from statistics, but it actually dates back even further to the 18th century in the Marquis de Condorcet. So let me give you the intuitive version of the model. You have some true ranking for the voter, which is this one. Now, in order to generate a noisy version of this ranking, what you do is you take every pair of alternatives and you throw a biased coin with bias p greater than 1/2. If it lands on heads, then you get them in the right order. If it lands on tails, you get them in the wrong order. So for example, I might compare Children's Hospital of Pittsburgh and Salvation Army, and I throw this coin, I get them in the right order, which means I'm going to rank Children's Hospital above Salvation Army, here at the bottom. I compare Children's Hospital and YMCA, I get them in the right order, but then I compare Children's Hospital and Meals on Wheels, and I get them in the wrong order, which means that I will rank Meals on Wheels above Children's Hospital. And let's say I get the other comparisons right. So this matrix leads to the ranking where Meals on Wheels is first, Children's Hospital second, then YMCA, and then Salvation Army.
don't have cycles?
Right, so you can definitely have cycles. So here you don't, like this is fine, unless I made a mistake, but generally you will usually have cycles. So the intuitive way to think about it is if you have a cycle restart. So think of it as just normalizing the probabilities so that you don't have cycles. There's a more mathematically elegant way of formulating it, which is the Mallows model, but I want to stick with the intuitive interpretation.
If the number of alternatives is large, you certainly will have
definitely.
Unless you take very high probability.
Sure. So, but just think of it as like normalizing the probabilities so that you end up with rankings.
Condition on sort of having
So let me just say a word. So the nicer way of formulating it is that the probability for ranking decreases exponentially with its Kendall-Tau distance from the true ranking, where Kendall-Tau distance is number of pairwise disagreements. Okay, so you just go over rankings and you normalize these probabilities and it works out.
Yeah, probability you need it exponentially, even if it's 1 over n squared.
Sure.
Already defined. You don't need exponentially large in n.
So the exponential is just like one way of formulating things, but you're in this model you normalize anyway. So any form that you take will work out in terms of giving you a probability distribution.
Experiments.
Anyways,
Sure.
But let's not worry about it, because really what I want you to take away from this is this depends on pairwise comparisons, which are kind of independent. And the reason I want you to think about this is that a compelling point to me is that the Mallows model is an unusually good fit with our setting. Like I said, it was introduced in the 18th century, and the Marquis de Condorcet thought of it as a model for political elections. So he said, there's a true ranking by quality of the political candidates, and voters want to do the right thing, but they make mistakes, and here's a model for how they make mistakes. That doesn't make sense to me because there's no true quality of political candidates. But even in recent years, people have looked at settings where there is a ground truth ranking, but then the way the structure of the noise works here is not well justified. In our setting, I think it's the most well justified that I've seen, because our machine learning algorithms take pairwise comparisons as input, and we measure their accuracy on pairwise comparisons. So the whole thing is built on pairwise comparisons, and it's very plausible to say, we are trying to predict pairwise comparisons, we're getting some of them right, some of them wrong, and that's the source of the noise. Of course, there are still some gaps. The model assumes the pairwise comparisons are independent. In our case, they're not completely independent. But nevertheless, this is as somebody who has worked with the Mallows model quite a bit in the past, this is an incredibly good fit with the Mallows model compared to previous applications.
What do you care about giving a linear ranking? If your inputs are pairwise comparisons and your output and your test time is pairwise comparisons, why not do pairwise comparisons? Predictions.
Yeah. That's a fair point. So usually in social choice, you think about rankings and voting. Voting rules by default are defined for rankings as input. A lot of voting rules also work with pairwise comparisons.
From a system point of view,
Yeah.
I can see the motivation.
Yeah, it's a fair point. Let's see. So, there's a bit of a subtle point I don't want to get too deeply into, but we.
Here is a short answer
Right.
that I would have been satisfied.
Okay, good.
Is
That's
that by going to the full ranking, you improve the pairwise, and this can happen, like big errors,
Yeah.
sort of, you're avoiding big errors because you're forcing a linear order.
right. Yeah. So I think that's actually a very. I think to make this more concrete, we would have to work a bit, but I believe that is the case. And one reason is that, the positive result that we see on the next slide shows robustness of Borda count. And that robustness basically relies on the fact that its alternatives won't wander away too much from their true position because you have to mess up many pairwise comparisons on the way, and that will not happen if you do it independently. Good, so, excellent, good. Okay, so with this, let's talk about the results. So like I said, for Borda count, we have a positive result, which is that for any true profile, it's unlikely the two alternatives would be ranked differently when Borda count is applied to the true profile and noisy profile. Now, Ishai will not be satisfied because I think this still doesn't answer your intuition before if this can't happen. So to make this a bit more formal, it depends on the difference in Borda scores. And to formulate exactly how, I require a few parameters of the model that I don't want to get into. But it's a very good result in the sense that even if the distance is relatively small, you will not flip the two alternatives. However, for a large family of rules called PMC rules, which are pairwise majority consistent rules, we have a negative result. This family also includes the Lull rule that we saw before and many others. So informally, what it says is there exists a true profile such that for any PMC rule F, it's likely the two alternatives would be ranked differently when F is applied to the true profile and the noisy profile. So this is a nice contrast because it says Borda is robust, but this is not an obvious thing. There's a very large family where we can show that they are not robust. So don't take it for granted. And
Can you just remind me what is Borda?
yeah, Borda is the one where you give n-1 points to the first place, n-2, or any way that you can shift the points if you want. And shifting the points will preserve this, this guarantee, of course. So partly for this reason, we did use Borda count in our implemented system. Okay, so at this point, I've told you how we implement the whole pipeline, and now we can automate decisions on this type of data. What we're doing here is very subtle, right? Because we're taking this participatory approach that hashes everybody's opinions together and goes through a lot of steps and outputs something. But it's very natural to ask, and 412 Food Rescue have asked us, so how well does this do on metrics that we care about? In order to answer that, they gave us a few months of data, so it's around 1,500 allocations with all of the data, which organizations were open at the time and so on, and the decision made by the human dispatcher, and we can check how well we do compared to the human dispatcher on various metrics. So we see the results are super encouraging. We do better across the board. Let me just show you two examples. So this is diversity of allocations, and what this is saying is, if you look at the bottom 30%, so the blue line is the human dispatcher. The bottom 30% of organizations receive nothing. The bottom 60% receive 10% of allocations, and the bottom 80% receive 30% of allocations. According to the algorithm, for example, the bottom 60% receive 30% of allocations. So this is not perfect. The perfect thing would be a straight line, but it's much better than the human dispatcher.
So all organizations are similar size?
No, the size is one of the things that are taken into account.
When you talk about fraction?
Oh, yeah, fraction is independent of size. It's just you get, you don't get. The size is actually...
What do you mean?
Perfect would be a straight line. If some of them are very big, they should get more than the small ones, right?
Yeah, depending on your viewpoint. So this is just like treating all organizations equally. You can think about a random allocation, which we have looked at. By the way, even that is not a straight line, even with large numbers, because some organizations are not open at some times. So it's not actually doing it like at random among all organizations.
But this was not your objective function to begin with.
Right, so we don't have a single objective function. If we just care about this, we would do random allocation. If we just cared about the next thing, which is driving distance, we would just optimize driving distance. So there's something a lot more subtle going on here, but nevertheless, it's a very nice sanity check to make sure that we're doing better than the human dispatcher. One reason why this happens is that we have access to all of the data, whereas the human dispatcher is overworked. So her name is Jen, she just, presumably in many cases, she knows some organization is open right now, and they usually pick up the phone, so she would call that organization. So of course, like many shortcuts can happen that way, whereas, the declared purpose of the system is that you have access to all of the information, you can make decisions based on all of the information. So the second thing is travel distance. And by just eyeballing this, you can see that the algorithm is doing better than the human dispatcher. There's a much larger spike around smaller distances. And in fact, the average travel distance for the algorithm is 5.5 miles. For the human dispatcher, it's 6.15. So we do see a significant difference. Okay, so almost the last thing I want to show you is just the final step of this, which is we are in the process of integrating the system into the 412 Food Rescue web interface. There is a whole lot of intellectual property barriers which are being worked through. But the key point here is that we're designing the system not as a way of automating the decisions and cutting the human out, but as a decision support tool. So the idea is that the human dispatcher will get recommendations and then decide whether or how to implement them. So the way it's designed is at the bottom, there's the ranking of the organizations according to the output of the aggregation step. If you click one of the organizations, you can get information about why Borda ranked that organization relatively highly. Okay, but it's very clear how Borda works, and you can also get information about why Borda chose a particular alternative, which makes everything more trustworthy. And this shows up in participant feedback. So Min and her team collected a lot of feedback from the participants over a year, and it's been, again, like very encouraging. So I'll just give you a couple of examples from each stakeholder group. One of the donors, for example, said that this seems quite a bit better than the human dispatcher. If organizations are literally getting forgotten about, which we know from the previous slide, from 2 slides ago, then this is huge. One of the volunteers said that this is certainly more fair than somebody sitting at a desk trying to figure it out on their own. It should be the most fair you could get. And this was representative of a larger set of comments of people who felt that the democratic approach is really using everybody's brain power and getting the best positive results. Another class of comments was people who were very suspicious of algorithms in general, but grew to trust the algorithm over the course of the process. And I think a lot of credit here goes to Min and her team and the way they worked with the participants. But for example, one employee said that seeing how the algorithm's construction was broken down into steps and just taking each one at a time made it attainable. We saw even more extreme comments of somebody who was completely distrustful of algorithms initially, and at the end said that he trusts the algorithm wholeheartedly. So there was a very big difference over the course of work on this. Finally, a very nice step that we had at the end is showing participants, each other's models and the output of the system. And we saw that that really increases people's trust in 412 Food Rescue itself and in the whole endeavor, like what they're doing together. So one nice comment was from one of the recipient organizations who said that no matter what group or individual we're feeding, we have the same regard for the food and individuals we're serving. And this, again, was representative of a bunch of comments saying, oh, this really made me realize we're all working together towards the same goal and makes me even more committed to the cause.
No negative feedback?
Right, so,
It was down when
yeah. No, yeah, so there were, let's see. There was I think the positive feedback way outweighed the negative feedback. I think there were, let's see, I remember there was still, some lingering suspicion of algorithms. Yeah, I don't have the negative feedback off the top of my head, but it was very limited. So we have in the paper like 1 or 2 comments that were kind of leaning negative. Overall, I would say, very positive.
But if you have only, 3 overworked employees, I imagine that any optimization algorithm with a clear objective function will also improve.
Sure. So, I mean, that is something that would be interesting if we can go through this whole pipeline and test some other objective. It would be a huge amount of work. Like I said, one reason I believe, and also based on the feedback, why this was so successful is the fact that you do have this democratic approach of everybody working together, like this comment on the green side, and we've seen many of these comments. So I think this, this has a couple of benefits. Both people buy into the idea of working together and making decisions. It also gives us a way of explaining decisions because we aggregate using Borda count. We can explain why Borda count makes the decisions it does. And I think that played a big role in people being willing to accept the result of the algorithm, including growing a lot more trusting of algorithms in general. So, if somebody, you could run this over a year and see what happens, but based on the feedback we got and the results we got, I suspect that it wouldn't do nearly as well as this approach.
Some aspects of the decision clearly depend on people's opinion. I mean, the quality of the organization, the recipient organization, but I mean, the need, the inherent need that the recipient organization is meeting.
Yeah.
And other things like minimizing travel time, asking people to do that is silly. Right? You can write a flow.
Oh, sure.
So
yeah.
seems to be a
So,
mixed.
so it's not that people are actually minimizing travel time. The people are weighing travel time as one of 7 features when they give pairwise comparisons. Our system is the one that scores travel time together with other stuff, gives rankings and aggregates them. So the optimization is done in a pretty implicit way, but by the system, right? That people just basically tell you how much do I care about travel time being short versus something else when they do pairwise comparisons in the beginning. Okay? And that's also, I think, partially why we get lower travel time than the human dispatcher, for example. Okay, so take-home message. We talked about virtual democracy. That's the main thing I want you to take away. You can think of it as people plus machine learning plus social choice equals a way of automating ethical decisions that's effective. We saw that we get great feedback from participants and really nice results on metrics. It's practical. We've built these 2 systems. They work well. And it's transparent. We just talked about it. I think the fact that you can explain to people how the whole approach works, why the system makes certain decisions. Of course, this is a big issue in ethical AI in general, but I think this is a big source of the power of the system and why it was successful. So let me just finish with the bibliography. The talk was based on 3 papers. The autonomous vehicle part is based on work with Ritesh Nutigato, Neil Gaikwad, Edmond Awad, Sohan D'Souza, Yad Rahwan, Pradeep Ravikumar in IIII 18. The HCI components of the food rescue stuff is based on work with Min-Kyung Lee, Anson Kang, Ritesh Nutigato, Alex Psomas, and a team of undergraduates that worked with Min. And the statistical stuff about robustness is a forthcoming paper in ICML, which will be presented next week, I guess, with Anson Kang, Min-Kyung Lee, and Alex Psomas. Thanks a lot.
So I guess the system is still oriented versus one decision. Like you learn only one decision. Like you cannot
Yes.
learn, say, faculty members and then don't have faculty meetings because it just
Yeah.
you can vote automatically, or in the next case, like the parliament,
Right.
just
Right.
learn the parliament and don't.
Yeah. Absolutely.
We got stuck with the elections.
Right. It's like if we could only automate these elections.
Elections like
Right.
in 1 second.
Yeah. Absolutely.
If it doesn't work, you can do it again.
Yeah. Absolutely. So the data collection. I just randomize again. Yeah. So the data collection is specific to a certain dilemma. The models are specific to that kind of dilemma. I just had a really interesting discussion with an HCI person from CMU, Nikki Kitur, in a 4-hour drive partially about this. Like, is there any hope of generalizing from one domain to another? I'm not too optimistic. I mean, so I think for any type of decision you want to use this for, right now the idea is to go through the whole pipeline for that particular decision. Yeah.
Isn't there a danger that the algorithm, let's say for Trolley Problem, will have discrimination, for instance, in some features?
That's a good question. So, and it's also something that, of course, people in machine learning worry about a lot in recent years, the whole issue of fairness in machine learning. So I think in this particular approach, I don't think of it as a major concern. And the reason is twofold. Let's, for example, focus more on the autonomous vehicle domain. There are many issues. Let's think about the food rescue domain. So the features that you take into account, of course, there is correlation between, you can say there might be correlation between race and poverty level in the area and so on. But, with these 7 features, it's very hard to encode biases into these features. Second, the only thing you do is report pairwise comparisons, right? So encoding your biases into the pairwise comparisons in a way that in the output of the aggregation step, these biases will play a role. It's so many steps removed from the actual input the voters give that I think I don't view it as a major issue for this particular application. That said, for other implementations, it's something you would have to rethink, right? Depending on the features and what exactly are the concerns.
What are the 7 features that you mentioned for the food?
Right, so 7 features were the number of clients served, food access, poverty rate, income level, driving distance, the number of donations received in the last 3 months, and when was the last time a donation was received. So these are features that A, people care about, and B, we have data for. Right? There might be other features you might care about, like how effective is the algorithm, as the organization distributing food, but that's not something that 412 Food Rescue has data for.
But some of the features, like you take from somewhere else, like poverty level,
Yeah.
I assume you're not...
Yeah, so that's from a database, yeah. Right. Yeah, so all of these, like, the level of food access.
So this can have hidden biases somehow. Poverty.
Oh, I mean, if somebody in USDA defines the level of food access.
It could be like, not someone bad.
Right.
When we define things, we have a downstream effect on you also, right?
Yes.
Like in Israel, poverty level is defined as a certain percentage of the average income.
Yeah.
If you switch to a system in which depends on, let's say, how much food does a person have,
Yeah.
you get fairly different results.
Yeah, fair point, conceivably. Yeah.
I want to open up questions on the philosophical.
Okay.
And you equated ethical and voting.
Okay, let's.
Because you said
I don't want to agree at this point.
that
But,
by voting you
Yeah.
can achieve ethical.
Right.
You have this in the slide. That you
Yeah,
showed
so,
in front of us.
right. So I guess the way I want to think about it is using this voting-based approach, we can make decisions on ethical dilemmas. In the self-driving car domain, whether these decisions are ethical is definitely debatable. In the autonomous, in the food rescue domain, there are more concrete considerations, I would say. The 7 features include, kind of fairness and efficiency and so on. So I kind of use the word ethical conveniently to encompass all of these, but I wouldn't insist too much on saying, especially in the self-driving car domain, it makes decisions that I can definitely say are ethical. It makes decisions on ethical dilemmas, and we can argue about whether they are ethical or not.
Yeah, because I think that's it's a major point, because you can do voting inside a prison and ask is these decisions ethical, or you
Right.
have a bunch of billions and you have different. So I think the framing of that is something to be quite
Yeah.
dangerous.
Right, so I think I'm taking a bit of advantage of the fact that ethical AI in general is a very general term. So I think like one place where I had the word ethical is in the first slide, right? And putting ethical AI to the vote. But this ethical AI encompasses many issues like transparency, right? Many issues that this system does address. It doesn't necessarily imply that I would be able to make a very concrete case that every decision made by the system is ethical. Right, so there's definitely like a framing issue, but to some degree I am taking advantage of the vagueness of some of these concepts.
Because I'm trying to say, like the paper that you mentioned in Nature, they switched the result when people asked, "Are you in the vehicle? Are you observing?"
Oh, that was in Science 2 years before,
Science,
yeah.
The Science one.
Right.
So it really depends on who are you sampling, and so what
Right.
I'm saying is, based on that, the link to the ethical is.
Right, right. Yeah, and of course there are, so there are issues like the issue you bring up is this, depending on your viewpoint, you might think that it's ethical to do one thing or the other. If you're in the car, you might not want to kill the passengers if it's your family. So you're referring to a paper from 2016, also by Yad and his collaborators, that just asked people on Mechanical Turk, like, what would you do in these different situations? So that's different from the Nature paper that was 2 years later. That's one point, but there are also like very subtle issues with all of these decisions are like life or death, but somebody can be harmed if it's somebody who's an athlete and that would ruin their career. That is like, right? So there are so many issues that prevent us from making like truly ethical decisions in that domain right now. So I don't want to claim that these are like truly ethical decisions. It's more a proof of concept, I would say.
Okay.
Oh.